Mr. Gracious.
Yes, sir. Good evening, sir.
Yeah, good evening, sir.
How are you doing, sir?
I'm fine, sir.
Well done, sir.
Trust you are good.
Yes, I am.
Yeah. Sorry. I'm still waiting for others to join as
Yes.
well. I'm still waiting for our instructor to reply the message. I don't know.
Okay.
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 Let's just wait and see how it goes.
Right, sir.
Okay. Hello, Jekolia, welcome.
Thank you, sir.
We are still waiting for our instructor and waiting for others to join.
All right, sir.
Okay.
Yes, sir.
Hello, good evening, everyone. Sorry if you can hear me, just a thumbs up or can unmute. Yeah, good evening. Good evening, everyone. Thank you for joining us on our last day of our 3-day SOLIDWORK Simulation Bootcamp. So, unfortunately for us, I just spoke to our instructor today and he said he's on transit. He wouldn't be able to make it for today's class. So I'm forced to see a way to see how we can salvage this and then conclude today's class. So I'll be presenting on from where he stopped yesterday. I may not be able to do much solid work, but I'll just try to explain some of the fundamentals. I hope would be able to understand and then get value for today's class. So give me a few minutes, let me present my screen. Sorry, can you see my screen?
Yes.
Okay. Yeah, thank you very much. So basically, what we'll just be doing today is to try to put more perspective on all the areas of simulation that are in SolidWorks. We started our session by talking about static stress analysis, and our instructor was able to demonstrate how you could perform static stress analysis. And there are a lot more other analysis that you could do in SolidWorks depending on the case, or should I say the scenario that you are faced with. Now, basically what I will just be doing is to try to explain each of these analysis. So the second analysis you could do is what's called the displacement analysis. I'm so sorry that I would not be able to demonstrate all this because it's not like I planned a CAD model to use for this. It just came unplanned. So I don't have a CAD model I could use to display all this. I've not properly prepared for this, so pardon me. So our displacement analysis, most times when you are faced with scenarios where you need to know if a part will bend or it will bend when a certain amount of load is applied on it. The static analysis we did yesterday was to tell us at what point will this particular load will it break? You understand? That's what our static analysis was able to tell us. But when it comes to your displacement analysis, it tells you at what point will your part bend, or at what point will it move. You can see, for example, let's say you were asked to design a particular bridge, and then you want to know when we apply this particular load, this bridge is going to be carrying this particular load. You want to know to what level of displacement will this particular bridge undergo. So go, you have to carry this bridge, a model of this bridge, and then do a displacement analysis. In that displacement analysis, you'll be able to see, okay, this is the level of displacement. And then from your experience, can you allow this level of displacement? So there are some bridges that after your analysis, you discover that with this amount of load crossing this bridge daily, you will have this amount of displacement or this level of displacement. And this level of displacement may not be permitted. So for that, you have to improve your trusses, or reduce the load, you understand, so that you can have an efficient design. Now, all these things depends in industry. For different industry, there are different factors of safety. When you're in the construction industry, there's a particular allowable factor of safety. When you are designing anything, you design with that particular factor of safety in mind. You understand? When you have your Normally in engineering, we know that when we have a factor of safety greater than one, we know that our our particular structure is safe. But then there are industry specific factor of safety that we apply to certain industry. We say, okay, it must be a factor of safety more than 3. Some industry, aerospace and the likes, they will say their factor of safety is 2. These are just to make sure that they over design this thing to fit the worst case scenario. So that's for displacement analysis. So the key ideas you need to understand about displacement analysis: your displacement results, they come from the same static studies that you do. It's not like you create um, another study. When you create your static study, after creating your static study, you can now generate a plot for your displacement analysis. So that plot is what now tells you the level of displacement that that particular structure undergoes undergo has undergone under that particular load. So that's what your displacement analysis you need to remember. Now, the next thing is that SolidWorks exaggerates the deformed shape on the screen by default. So it's visible, the true numeric value in the probe. So when you look at, after doing your analysis, you discover that you are able to see the level of displacement. But the truth of it is that in real life, you may not be able to see that displacement because it's very infinitesimal. So you cannot see the displacement. But SolidWorks has a way of increasing or exaggerating the displacement so that you can see it. But if you want it to display for the displacement to show naturally, you can actually tweak your probe, and then your displacement will show naturally. But the default setting for SolidWorks is that it exaggerates this displacement so that you can see it visibly on the software. So another thing is that for the probe tools to click a specific point and read its exact displacement. So after you calculate your displacement, you can actually know the level of displacement per different areas of your static analysis that you did. You can know the particular displacement at every area. So you can analyze, okay, this is the level of displacement we are having at this area of the trusses. Can we allow this displacement? If not, what do we do? Should we add more trusses, or should we reinforce, basically just reinforcing the structure to be able to withstand more much of the load and then reduce the displacement. So the next is that you compare displacement against a design tolerance. I'd already talked about that. Some industry have a particular factor of safety. Others other industries factor of safety is greater than the other. So you need a particular level of deflection for when maybe you are designing for a bridge. There's a particular allowable deflection that when you get in your analysis, it is allowed. But when your deflection start to go above that particular allowable deflection or tolerance, you know that you have to reinforce that particular structure. So that's all about static. I can display. Okay, I wish I can display. Okay, let me try. So okay, so let me try. Please, can you hear me? Can you hear me, everyone?
Yes, sir, we can hear you.
So I will try to switch. I will try to switch to SolidWorks so I show you how the static the displacement is. I may not be able to do that for every of the other topics because I did not actually prepared to present this. So bear with me. I just let me share my SolidWorks. I think I have a model I did a static analysis on. So we can just do the displacement, show the displacement. Okay. Sorry, a few minutes, please. Okay, so sorry, can you see my screen?
Yeah, okay.
Okay, so this is actually a pawn I designed for a particular analysis that we did. So let me actually I pray this analysis is still here. Okay, so I think the analysis is still here. I may have to run it again. Okay, it's fine. Sure. Sorry, it's going to take a while because so this is actually a topology optimization. So I can't. Okay, let me see. Okay, this is the static study. So this is your displacement. So if you look at this is your displacement analysis that you did on this static analysis. What we did was to apply a fixture under, and then this pawn actually it was under a load of 100 Newton. And after undergoing this load, you could see that from, okay, let me show the stress. Okay. So if you check the stress, this is the stress analysis. When you compare the von Mises stress to the actual material allowable stress, you discover that this this particular pawn can still undergo the applied load without totally deforming. So that was what we got from this analysis. But what I'm trying to show us today is just the displacement analysis. So this displacement analysis, when you generate your static study, It shows you your stress strain and your displacement analysis. From there, you'll be able to know the level of deflection. Now you can say you want to animate to see the deflection. So you can see this is the deflection when 100 Newton of force is applied on this. I told you this is exaggerated. This is not actually how it's going to show real life. It's not going to show like this real life. But the software is trying to make you see it visually that, okay, this is how it's going to displace. So that's that for displacements analysis, just to show you how it works. So let me switch back my slide to, okay. So that's that for our displacement analysis. So the next thing we are going to talk about is our thermal simulation. So basically, um, how does heat move through and out of a particular material? That's where you need to consider your thermal analysis. You need to check the heat distribution across a particular part or across a particular assembly. There's this, I designed a particular part recently for a client, and then I needed to show, okay, how will the heat be dissipated on that part? So I needed to do a static analysis at work, and then, do a thermal analysis at work, and then we're able to see, okay, this is how heat is going to be dissipated in this material. And from that analysis, we're able to inform the client that, okay, this is how he should go about this particular material. This is where he should apply his fan for cooling and all that. So basically, what thermal simulation, forgive me, does for you is to show you your temperature distribution across that material, depending on what you are trying to, your particular structure you are trying to do. Is it that how heat is escaping in that structure? Is it through conduction, convection, or radiation? I don't have a particular simulation here that I can show. I did not pre-plan this class. So forgive me if I don't have something to show us here on our thermal simulation. But then where this simulation actually matters is in our enclosures, probably our engine components, heat sinks in your laptops, your molds all need to manage heat. So this is where you apply your thermal analysis to see how the behavior of heat in these appliances or components, and then it will inform your decision on what next to do to mitigate um, um, areas of extreme heat. So that's basically all about thermal analysis. And then what you need to actually keep in mind is that steady state um, thermal assumes condition have settled, temperature no longer changes with time. So when it comes to thermal analysis, there are different type of, you can apply a steady state. That means your your temperature is not changing with respect to time. Your temperature is constant. So, but this is not in ideal. In ideal cases, temperature is not constant. It varies in different part of the um, material. So that's where your transient thermal analysis. That's where you check for changing temperatures. So also you can check your conversion coefficient that describe how efficiently your air or fluid carries heat away from the surface. So that also is something um, you need to take note of. Also, your thermal results can also feed into a thermal stress study to see if temperature change along cause dangerous expansion. So for different material, there's how they respond to temperature. So the way steel respond to temperature is not the same way plastic respond to temperature. Neither is it the same way aluminum or any other material respond to temperature. So the analysis results you get will tell you, okay, this is how this particular material and this particular structure respond to temperature. Now, that will now inform your design or your design choice or your design considerations. So that's all for our thermal simulation. I don't have, probably I'll share this slide with us. You can watch some of these videos to give you perspective on how to run the simulation on your software. So we also have frequency analysis. So okay, for this now, I think I have an experience with this. For I work in an aerospace company where we do analysis of a CubeSat. So we are trying to see how frequency, how distortion in natural frequency. You know, there's what we call resonance. When every material, or should I say every structure has its resonance frequency, or should I say its natural frequency. So when that object is vibrating beyond that natural frequency, we get what we call resonance. Now, that resonance, it can be okay and it cannot be okay. Now, for resource constrained environments like in space, where you have to deploy CubeSat in space, there's a particular frequency that when your object or your structure begin to resonate, that's I think 100 hertz. When your object begin to resonate above that frequency, your your structure will begin to fail. So you design to make sure that your structure doesn't resonate beyond that particular allowable frequency. So the object has its particular natural frequency, and you have a particular um, resonance frequency that is allowable. So with that, those particular consideration informs your decision that, okay, when I design this part, I will expose this part to varying frequencies and then see how it behaves. And then know, okay, this is the allowable frequency that this part can behave. Anything beyond this frequency, it will start to wobble, or it will start to behave violently. So you will see that in some particular, um, you see in scenarios where some movies, they will pitch their voices to a particular frequency, and then a glass will break. That is physics. It is because the molecules of that particular glass has been exposed to a frequency beyond its natural frequency, up to a point that it cannot withstand that frequency, that vibration, and then it breaks. I've heard of scenarios where they use this resonance, this frequency to demolish buildings, where you expose the particular building to a particular frequency, and then the building collapse. So if a machine part natural frequency matches the frequency of a motor, a fan, or a road nearby, resonance occur and vibration amplitude can grow dangerously large. This is how bridges, brackets, shaft fail from fatigue or sudden catastrophic vibration. Frequency analysis help you avoid that collision of frequencies. So you would not want your machine. What is basically telling you is that you will not want your two parts in a particular mode structure to be vibrating at the same frequency. At times, the changes in amplitude of vibration would cause a dangerous wobble effect in that part, and that would lead to a catastrophic failure, and which is something that we try as much as engineers. Sometimes you hear that they make the statement that engineers over design for scenarios like this. So what you need to, key ideas that you need to remember is that the lowest natural frequency, mode one, okay, there are two. I didn't explain. Okay, I explained it, but I didn't actually explain each of these. So when it comes to frequency, they categorize them into different modes, which is the mode one, mode two, mode three. There are particular frequency ranges for each mode. I didn't write them down. Sorry. So that frequency mode tells you what particular mode you are, and depending on that, the mode that you are, you'll know if your part is vibrating at a natural frequency or is vibrating above its natural frequency. And that makes the engineer to know, okay, we need to tune this frequency down. We need to do something to tune this particular part, its frequency of vibration down. So fixtures change natural frequency. A free floating part vibrates differently than a bolted down one. So most times, what this is trying to tell you is that most times when you have your part to be vibrating at you discover that your part is vibrating at a particular frequency, and then you want to make the part not to vibrate at that particular frequency. All you need to do is to add more fixtures, add maybe bracket or something. Sometimes I think I did a design at work where we needed to add a dummy load inside the CubeSat to be able to balance the weight and as well reduce the frequency of oscillation. So that's actually some of the techniques that you need to do at times to make sure that you have distributed frequencies across your particular design. So I don't have an analysis here for us to go through or do something about this. Probably, and I didn't even know if your instructor had something outlined for today, but then all is well. We'll try to just salvage the class. So please, can you hear me?
Yeah,
Hello, guys.
Yes, we
Yeah.
can hear you.
Okay. Thank you very much. So the next thing we are going to be talking about is the buckling analysis. So the first analysis we talked about static analysis, we talked about displacement analysis, we talked about our thermal analysis. Now we are talking about our buckling analysis. Now, buckling analysis, what it actually does for you is that when you have a part, you want to know, will that part, how will it compress? How will that part compress? You understand? Is it compressing sideways? Is it compressing to the left or to the right? That's where your buckling analysis comes. And with your buckling analysis, you can tell from a straight part, you perform an analysis on it, apply a load. It's more like your static analysis. But then, sorry. So it's more like you are applying varying compression load, and then you are seeing at what particular point will that part begin to bend. So buckling analysis predicts the load at which a slender part like a column, maybe a column in a bridge or in a house, a thin panel or a long strout will suddenly bow or collapse sideways. A failure mode that can happen well before the material itself would yield in static study. So at times you may be asking, okay, what's the difference between a static study and a buckling analysis? They are actually there's a difference. You know, before your parts undergo either a plastic deformation or a break, it will first of all bend before it undergo static or I mean plastic deformation. It will bend. So now the thing is that, or before it breaks, it will undergo a particular deformation. So what you need to do, what your buckling analysis does, is to show you, okay, the degree of that bending, and then where will it be bending to. So you now know, okay, this is what we are going to be undergoing. There are times that in a particular structure, you actually need that structure to bend. There are scenarios that you need it to bend. It's not like it's every scenario that you want your structure to be rigid, to be strong. There are scenarios that you are actually designing for that structure to bend, but then you don't want it to bend too much. Let's say in your biometric strip that is inside your iron, there's a particular strip that is inside your iron, and when that strip undergoes a certain temperature, it bends. And then you want to know the limit of bending that biometric strip undergo. Now, that's where your buckling analysis comes. Your buckling analysis tells you, okay, this is the level under this particular load. This is the level that this thing is going to bend up to. So you design with that bending, that level of bend in mind. So that's much I can say about buckling analysis. I haven't done much analysis on buckling yet. Something that I will try. So basically, buckling analysis is done by mainly people in automobile or aerospace analysis. They do that a lot to be able to see how, okay, when your car they jam each other. When you're in an accident and two cars jam each other, you want to be able to tell, okay, what's the degree of bending that will occur when these structures jam each other. And that's where buckling analysis come into. Now, the key ideas you need to remember in this analysis is the buckling load factor. Multiply your applied load by the buckling load factor to find the load that will trigger buckling. So when you multiply your applied load to your buckling load factor, you will know that, okay, if I apply this particular load, this is what will trigger the parts to buckle. Another thing you need to remember is that your buckling load factor, when it is greater than 1, means buckling happens above your applied load. You understand? So, but when it is less than that, you know that when you apply that particular load, your buckling will not happen. So buckling only matters for compressive load on slender geometry. So you may be asking, where do I use buckling analysis? So basically for columns, for beams, for structures that are slender. And what you are not looking for your tensile load. Much of what you are trying to see is your compression, how it compresses under that load. So it's a concern for tension or for bulky, stocky parts. So now you compare your buckling results against your static stress study to see which failure mode governs, either yielding or buckling. So I think there are scenarios that you want to know if it is buckling that will take precedence or it is yielding. That's your static analysis that will take precedence. Like I said, there are times that you need compression in your structure. I think for your rail, your railroads, you actually, there's a particular level of compression that you need the material there to always compress, and come back to its natural state. That's, it expands and contrasts. So you need that. You don't want it to just be static. So you need to do an analysis to be sure that, okay, this part is actually doing this and that. Now, the next one we are going to be talking about is our fatigue analysis. So you may be asking, what's the difference between our static analysis and our fatigue analysis? Because it's basically almost the same thing, but your fatigue analysis is basically telling you, you may be wondering, okay, for materials or for products, how do you know the life cycle of a particular product? Because that product under a particular certain year or under a certain period will be undergoing varying load. And then you want to calculate that the varying load or varying stress on that part over 5 years, over a particular number. So you would have to do a fatigue analysis to see, okay, when I constantly apply this load for so time or for so amplitude, what is the level of fatigue that this part can withstand? So with that analysis, you are able to predict how many loading cycle that part can undergo. So if it can undergo maybe 1,000 loading cycle, you will know that, okay, under the course of its life cycle, it can undergo 1,000 load cycle before it collapse or before it bends. So that's what your fatigue analysis helps you to do. A part, they said a part can survive before it cracks. That's under repeated loads. It can survive. You want to know whether it can survive before it cracks, even when each individual cycle stress is well below the natural yield strength. So you may be saying that, oh, when I apply this load on this part, it is still not yielding. That means on your static study, the part is not breaking, it's not yielding. But then how long can I keep applying this particular load before this part breaks or before it cracks? So that's where your fatigue analysis comes into play. So why fatigue analysis actually matter is that most real world failure, like cracked brackets, broken spring, a snapped shaft, happens from repeated loading over time, not a single overload event. A part can pass a static study with a great factor of safety and still fail after 50,000 cycles of vibration or use. So like I explained, you can pass your static study, but still yet, because that part will be used for a long time, you have to calculate, okay, how long can we apply this particular load for us to know if this part is going to withstand that, for us to know, okay, this is how many times this part can withstand this load before it breaks or bends. So that's the key idea about your statics study. I mean, your fatigue study. So your fatigue study builds upon top of one or more existing static or other studies. You don't start from a blank model, like I said. So you need your fatigue, your static study to be able to know your fatigue, to do your fatigue study, because it's more like you are applying that same load for a varying amount of time, or that same load repeatedly. So you are not changing anything from your static study, but then you are trying to do your static study for a longer time to see, okay, when I apply this load repeatedly, how does it behave? So that's where your fatigue study comes to play. Now, results are typically read as percentage damage per event and life. So number of cycle below failure. So there's a particular number of cycle before your part fails. So when you do your static study, you will know, okay, when we apply 50,000 cycles of this load repeatedly, this part will fail or not. So let's say you manufacture a particular product, and then there's no way for you to use that product for 10 years for you to know if that product will withstand um would last 10 years. But then with your fatigue study, you can be able to see, okay, when I apply consistently this amount of load for 5,000 cycles or any other cycles, this is what I will get. This part can withstand it for this amount of cycles. And then if you can withstand it for this amount of cycle, you can actually interpolate it to know, okay, for 5 years or for each year, this is the particular work cycle that this product can go. And then you can calculate if this product will last or not. So that's now in your fatigue study, your SN curve, that's your stress versus your number of cycle. You need to know how to read this curve. And this is where your fatigue study is going to be. And then when you read this plot, you'll be able to see, okay, this is how stress is varying across the cycles of your load applied. Now, below the material endurance limit, many metals can theoretically survive near infinite cycle. So, like I said, below your material yield strength, you can consistently apply load, and then you see that your material can easily survive it. But when you start going above that yield strength, you will see that there's basically there's not a uniform deformation across that material. So that's where you actually need to know that in your design before concluding that, okay, this part can survive 10 years, 5 years or so. So the next thing we are going to talk about is our flow simulation. So your flow simulation, please, can you hear me? Hello guys, yeah, thank you. So your flow simulation what it does for you is fluid or air. If you remember in your mechanics or your fluid dynamics, they said they compare air and fluid in your continuums principle, that there's how they behave. When you are trying to study the behavior of fluid, it can be airflow or fluid flow. When you are trying to study the behavior of that fluid on a particular material or on a particular surface, that's where your CFD, they call it, the short name is CFD, but it's actually flow simulation. So computational fluid dynamics, you are trying to see how air is flowing across this material, or see how fluid is flowing across this. And best scenarios for these are people that do aerofoil, maybe in the aerospace industry or even in the marine industry. So they actually need to see how, even in the aerospace automobile industry as well. So you see how air reacts and fluid reacts on your particular product before you can now go ahead to prototype that product, and then manufacture it and say, okay, this product can actually work in this area efficiently. You can actually test how efficient it is on your software before you start manufacturing. And this is where your SolidWorks flow simulation, it's actually, it's like a plugin on your SolidWorks. There are several other plugins like that. It's one of them that helps you to carry out flow simulation. So basically, you are trying to see how pressure difference, velocity, and temperature affect your particular material. Now, why this matters is that anything involving airflow, cooling, drag, or fluid movement benefit from CFD. That's computational fluid dynamics. Your car, your drone dynamics, your HVAC, your pump, and your valve design, electronics, cooling, pipe flow, etc. They survive, or they behave, they react to changing flows or changing fluid flows. So you need to be able to see in your analysis how this thing reacts to these changing fluid flows before you start designing. So in retrospect, before we had simulation softwares, people or engineers would have to design that product and then start testing it in turbine, in I mean in our, yeah, in our turbines. That's our, they call it the, sorry, I've forgotten the name. It's like a simulated environment for testing how your material undergoes air flows or fluid flow. So they'll have to test it in those environments to see how they behave. But with our softwares now, we don't necessarily have to test them in those environments. First of all, we can test them on our software to see how they behave to changing fluid flow or air flows before we now build prototypes and then use those prototypes to validate our tests that we've done on the software. And then we can now go ahead to manufacture. It reduces the development time and then the drudgery in 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 production, or should I say in prototyping, and also the cost as well. So one of the key things you need to remember that flow simulation, they are separate add-ons. For some of you that are using SolidWorks, maybe student version, you may not have all the simulations, or you may just have some of them. So you may be wondering, why don't you have it? It's because it's an add-on, and then as an add-on, it may be paid. Maybe you need to pay for some of these subscriptions for you to have some of these add-ons, while some of them are actually, they come with student version. So you define a computational domain, your boundary conditions for your fluid or your airflow. That's actually what you do in your analysis. Like I said, I didn't prepare for this, so I didn't have like an analysis in store. I was thinking our instructor would do that, but unfortunately, an emergency came up for him. So the next thing is, results include velocity and pressure plots, streamlines, part fluid particles flow, and forces drag and lift. So in your results, you will get all this. So it is now, most of the times, what you do as engineers is to use this software, and your ability to interpret what this software gives you at the end of the day is what makes you a good engineer. You understand? Your ability to interpret this, your airflows, your drag results, and your pressure plots is what makes you a good engineer. So it's not just using the software to generate it, but do you know what they mean? So that's another topic for another day. So mesh refinement near the object matters a lot in CFD. For me, I don't do much of CFD because my work doesn't demand CFD. So, but for someone that does more CFD, he would be able to know the mesh requirements that he needs. You understand? Like your instructor talked about that. He talks about FE analysis, the finite elements analysis, that your particular structure is discretized, broken into small meshes, and then it is from those small meshes that you now analyze and get to know how fluid or airflow behaves on that material. But different industry has the level of fine or coarse refinements that you need to do to get an accurate result. So that's something that as an engineer you need to know to be able to get an accurate result. The next thing we are going to be talking about, which is I think the last topic. Yeah, yeah. So the next thing that we are going to talk about is design optimization. So some persons call it topology optimization. So most times after designing, after doing your static analysis, doing all these analysis, basically for a start, your static analysis, you may have to do a topology optimization. Okay, sorry. Okay, I'm talking about design optimization. So design optimization and topology optimization, they are different. They are different. But for design optimization, you are actually designing after putting your design under the varying static or any other analysis. You have gotten your results. Your ability to use those results to now reinforce your design, optimize your design your case for your case or your scenario is very important. And that's where design optimization comes to play. What's the lightest, the strongest, or the cheapest version of this part that can still work? So for static study, we may have to, for solid objects, we may have to do a topology optimization on that part to see, okay, these are the areas that we need to reduce material to be able to save cost, and then design a cheaper and a lighter part that can withstand the required loading condition and still do it functional and still be functional. So that's where your design optimization in terms of topology optimization comes to play. So like I said, in different industries, they have varying factors of safeties and varying, should I call it, varying level of deflections that you need to have. Your ability to know each level of deflection that you need for the required products that you are designing is very important, so that when you know that deflection, when your material deflect above that deflection, you know if, okay, we need to do something or not. You know if you cannot, you need to optimize that part so that it doesn't deflect. So those variables are very important in your design. For me, let me use my own day-to-day work that I do in the space industry. Is mainly I design space systems. Basically, what the project I'm currently working on are CubeSats. So I need to know my design requirements. So my design requirements helps me to be able to design to that requirement. For example, for a CubeSat, they have form factors and they have a particular loading conditions that CubeSat is supposed to withstand. So my ability to design to make sure that my design is optimized for that loading condition, and I also have a particular safety net that even if I apply more than that loading condition, like I said, designers or engineers, we we over design for extreme cases, my parts will still be able to withstand or will still be able to survive. Like a popular slogan for us in our industry is we are designing for a resource constrained environment. In simple terms, we are designing for an environment that we don't know. And the resources available in that environment is, to a large extent, is not known to us. And we have to work with what we know about that environment. And as much design for the extreme cases that we don't know of. So we have to be very careful in our analysis and then very careful in the outcomes of those analyses. Because like I said, your softwares are garbage in, garbage out. They give you what you impute in them. So your knowledge of what you are imputing and then the outcome that you are expecting is actually very important for you to be able to make critical decisions that will help you get your end results. So that's that aside, I think we've done justice to what I have to present to us today. I'm so sorry that we're unable to get our instructor to take up today's session and then practically demonstrate most of these analysis. You understand? But I hope that with what I've explained, you have been able to pick one or two things about this analysis and you can go further to do your research. And then I have courses or materials that can support your learning journey. And then probably in subsequent boot camps, the truth of it is that we cannot um, exhaust all the analysis in this 3 days boot camp because there are a lot of things in those but this is just to give you an overview of the analysis that as an engineer you need to be aware of and then you need to familiarize yourself with so that you can be able to be a better engineer. So I'll be dropping the link to today's attendance on the call so you can fill your attendance. If you have any question, now is the best time to ask your questions. I'll do my best to answer the questions to the best of my knowledge. And then where I don't have an answer for you, I can say, okay, I don't have an answer. Probably I'll research that and get back to you. So go ahead if you have any questions. Let me quickly get the attendance form. So I just posted the attendance on the link on the chat. You can please fill in the attendance. Any question, anyone? Okay. So without any more question, we are coming to the end of today's lecture, or should I say today's boot camp. Thank you everyone for joining. We'll be having we'll be having subsequent webinars. And one of them is we'll be having a webinar in the aerospace industry. Someone is going to come and then teach us how to design aircrafts and drones and all that. That will be our next webinar for this month or probably next month. So look out for that. For those of you that are in the aerospace industry and you want to see how SolidWorks is using the aerospace industry to design aircrafts and all that. So this is a good time to come and ask any of the questions that you have and then possibly see how aerospace engineers or designers use SolidWorks to design. So thank you everyone for joining today's bootcamp. please fill your attendance. We have 3 minutes for you to fill your attendance, and I will drop the call. Thank you everyone for joining today's bootcamp. Thank you very much. We have 1 more minute left. I'll be dropping the call. Please, I mean, the link to today's call will be dropped. I mean, the YouTube link will be dropped. So for those of you that want to rewatch and then pick one or two things, you can as well check on the link later on and watch. And subsequent links have been dropped. So you can watch them and then properly understand what we have taught on in these 3 days of SOLIDWORKS Simulation Bootcamp. So thank you everyone. Have a wonderful evening. Thank you for your time. Good night.